Now I like to call Professor from Department of Civil Engineering, IIT Kharagpur, to deliver a lecture on biological and bio-electrochemical wastewater treatment technologies and their efficacy for imparting sustainability to the wastewater treatment. So I like to call Dr. Milind Kulkarni sir to briefly discuss sport.
So friends, we are very lucky to have Professor Makrand Ghangrekar with us. He is professor in Department of Civil Engineering at Indian Institute of Technology, Kharagpur. So another introduction is he is my good friend at IIT Bombay. We did together PhD in Environmental Engineering from IIT Bombay. So he is Institute Chair Professor, Fellow INAE member, European Academy of Sciences and Arts, MASC, former head of School of Environmental Science and Engineering, former head PK Sinha Center for Bioenergy, and professor in charge Aditya Chaubey Center for Rewater Research at Indian Institute of Technology, Kharagpur. So he had been visiting scientist to Ben Gurion University, Israel, University of Newcastle upon Tyne, UK under Marie Curie Fellowship by European Union, and had stint as faculty of various capacities in renowned engineering colleges and research institutes. He has been working in the field of anaerobic wastewater treatment, bioenergy recovery during wastewater treatment using microbial fuel cell and bioelectric chemical systems. So I can give go on for giving his introduction for another 15 minutes, but for paucity of time, I request my friend Professor Makrand Ghangrekar to continue with his presentation. Thank you.
Thank you, Professor Milin. Okay, thank you. So, very good afternoon to all of you, and thank you, Dr. Milin Kulkarni, for giving me opportunity to present the work that we are doing on imparting sustainability to the wastewater treatment at IIT Kharagpur. So, friends, we are all aware that the water scarcity and availability of fresh water is reducing day by day, and in 2025, it is expected to remain around 5,700 meter cube per capita. So, to fulfill this gap and to reduce the stress on the fresh water, we need to find out alternate source. So sewage can become a sewage, that is municipal wastewater can become a assured source irrespective of the season. This quantity of water is generated in every urban area, and if we provide proper treatment to that part, we can produce reusable quality treated water. In a conventional sewage treatment plant, mostly it comprises of primary and secondary treatment, and tertiary treatment is absent. But tertiary treatment is really required to produce reusable quality treated water out of municipal wastewater. The statistics, the Indian scenario is something like this, that about 38% of the sewage generated in this country is being properly treated before disposal, and remaining is being discharged untreated into water body. So, though the government is very aggressive in erecting the sewerage infrastructure, but still, because of the rapid rate at which the urbanization is happening, so we are lacking in this infrastructure. And to make treated water out of municipal wastewater available for public users, various non-potable uses, we need to also find out the technologies which are affordable and can give reliable performance as well as they are cost effective. The concern here again is the emergence of the emerging contaminants. So these are personal care products, antibiotics, the painkillers, and other solvents that we are using in day-to-day life. They are appearing in the trace concentration in the sewage, and they are difficult to remove with the primary and secondary treatment. These compounds remain almost untouched, and hence a proper tertiary treatment is required to produce safe water for downstream reuse. We are all aware the primary and secondary treatment, what is it, and then what is the need for tertiary treatment. Primary treatment is meant for removal of suspended solids as well as floating matter. The secondary treatment further removes colloidal as well as soluble organic matter, either using aerobic or anaerobic processes. And in the process, the biological treatment, the sludge that is being generated gets stabilized. However, the secondary treated effluent will not be having the quality suitable for downstream reuse, and hence further treatment may be required for removal of organic matter, removal of nutrients, removal of turbidity, removal of pathogenic microorganisms typically present in it. Color and odor is mostly due to presence of organic matter, and it will get removed once we remove organic matter. And also we need to think of removal of emerging contaminants, which is a major challenge, and interest scientists are showing developing different technologies, advanced oxidation process for removal of these contaminants. National Green Tribunal has given very ambitious target in 2019. For mega and metro cities, the BOD should be restricted to 10, COD 50, total nitrogen 10, and total phosphorus 1. We have adopted these standards by now. Very soon, we need to equip our existing wastewater treatment infrastructure to these guidelines. Hello. Yeah. So the drawbacks of conventional sewage treatment plants are inability to remove organic matter to the least extent. I mean, to produce effluent with that is free from organic matter, and we require further treatment for pathogens removal, removal of emerging contaminants, nutrients, etc. So we all know that reverse osmosis, which is employed in developed nations for treatment of secondary effluent, is capable of producing the water free from almost all these pollutants. However, at very high cost. My experience is the cost of employing RO, reverse osmosis, would be of the order of rupees 30 to rupees 50 per kiloliter of the water that we process. And also in the process, reject that is generated. So reject management is also an issue by employing RO. So instead, we need to look forward for mid or low energy consuming technologies. At the same time, the reliable technologies which will give misproduce the treated wastewater at the affordable cost. So if we really invent into the tertiary treatment processes which are affordable, so that will produce reusable quality treated water at the affordable cost. It will reduce the stress on the fresh water demand. So to achieve that, we can explore algal technologies so that the harvested algae can be used as a feedstock for biofuels. We can use the concept in the bio-electrochemical systems, the specific configuration microbial fuel cell, to where the wastewater itself can work as a fuel, and a one-step electricity can be recovered. We can explore possibility of sewage sludge conversion into activated biochar or hydrochar. This char itself can be used for tertiary treatment or can be used for the industrial treatment and many other industrial applications. This biochar or hydrochar can be used. Methane recovery from the wastewater is almost mature technology now, and most of the industries are, and even municipalities are having anaerobic reactor for recovery of methane as a first stage treatment. Aquaculture can also be practiced in the partially treated or treated sewage so that it will fetch us additional revenue from the sale of fish. And upcoming technologies since last 10 years, scientists are focusing on microbial electrosynthesis, where apart from wastewater treatment, the CO2 that is released in oxidation of organic matter can be utilized for synthesis of carbon chemicals. So by exploring these possibilities, we can impart sustainability to the wastewater treatment. And here onward, I will quickly take you through the works that we have done at IIT Kharagpur. In 2014, we installed 400 meter per day capacity USB reactor. This USB reactor meant for removal of organic matter from the sewage generated on campus. We typically have very dilute concentration of the sewage. COD annual average around 230 milligram per liter. So while treating such a low strength wastewater, biomass granulation have not been reported anywhere other than this plant. So we have about two-thirds of the biomass in the granular form in the USB reactor, and then the effluent of the USB reactor is getting treated in the high rate algal pond. So by properly designing the mixing conditions in the reactor is maintained at the optimum so that it supports biomass granulation, and this way we are getting very high treatment efficiency. Though initially it took us 5 months for commissioning USB reactor to reach to the applicable COD removal efficiency. But since then, in winter, this reactor gives around 68 to 70% total COD removal efficiency, and in summer, the efficiency goes around 77 to 78% for total COD removal from the dilute wastewater which is generated on campus. And then high-rate algal pond contributes further for nitrogen and phosphorus removal with more than 85% nitrogen as well as nearly 90% phosphorus removal. And on the top of it, it helps in reducing the algal cultivation, raises the pH to 9, and that helps in reducing 2 to 3 log scale pathogens. So this way, that time, 2014-15, the effluent generated was meeting the region norms for less than 1000 mpn per 100 ml, and this water, treated water, we were using it for horticulture purpose. However, with the stringent norms coming up in 2020, we developed another 300 cubic meter modular sewage treatment plant comprising of anoxic MBBR followed by aerobic MBBR. This nitrified effluent of aerobic MBBR recycled back to anoxic MBBR, and then it goes to lamella clarifier, and then dual media filter, and we have three-stage disinfection: ozonation, chlorination, and UV. So three-stage disinfection come advanced oxidation process so as to address those emerging contaminants. That is what our target was, and then finally ACF to trap any disinfection byproduct to produce safe the effluent safe for reuse. These are photographs of the plant, and a very ambitious target that we set with the COD 20 milligram per liter, BOD less than 3 milligram per liter, and MPN less than 3. So that the water is suitable for any non-potable reuse purpose on campus. And this is the performance. Soluble COD is yearly average around 18. Soluble BOD, sometimes we get BOD, most of the time it is 0. So 0 to 1. So less than 3 is we are easily achieving. Coliforms also, majorly it remains nil, but sometimes accidentally we may get one or two. So the overall, this treated water is meeting the expectation. But the problem is the presence of TOC. This TOC, when we give ozone dose of more than 5 milligram per liter, we can bring it down to below 10. But then that makes it a costly affair. So with the regular dose of 2 to 3 milligram per liter of ozone, the TOC gets elevated to 15 milligram per liter. And this TOC comprises of nearly 800 compounds, including antibiotics and the personal care products, the shampoos, and various other chemicals that we use in day-to-day life. And their presence in though in traces, microgram and nanogram per liter concentration, that is the only thing making the water not calling it as a potable purpose. Otherwise, potable quality water. Otherwise, this coliform, by maintaining it in proper order, this is really meeting close to the potable quality requirement. Having experienced in the 20s about the 300 cubic meter plant, the same concept we extended to develop 1.35 mld sewage treatment plant to treat the wastewater generated from the hostel nearby the hostel itself, so that the treated water can be used back in the hostel premises for horticulture, and also recharging the pond which is present on campus. We set up a target of keeping the life cycle cost of less than 15 rupees per kiloliter, and the similar treatment chain we use comprising of anoxic MBBR, aerobic MBBR, lamella clarifier, and then here UV we eliminated and we only installed chlorination and ozonation, and then followed by chlorination. So, and one is the ozonation tank, then chlorination tank, and this treated water reservoir from where the water is being pumped to the respective hostels back for horticulture. And this is the performance which will convince you the performance of this plant. So soluble COD typically less than 20 milligram per liter, total COD remain less than 30 milligram per liter. MPN also sometimes we do get accidentally, and it's 3 to 5 number, but it reasonably under control. NGT says 100 fecal coliforms. We are having total coliforms of 3 to 5. So the water quality is much superior than even the raw water which is available in the river, which we are accepting for our fulfilling our potable needs. So this quality is superior than the natural water quality available in the river. Then while evaluating the life cycle costing, we evaluated cost for primary and secondary treatment alone as a case 1, case 2, with primary secondary treatment followed by ozonation. Case 3, ozonation plus chlorination. Case 4, with ozonation and then UV. And case 5, all the three disinfection processes in place. What will be the cost of the treatment, considering all realistic cost of manpower, salaries, electricity, based on the capacity that is installed, replacement of the periodic replacement of the pumps, UV lamps, UV sleeves, media of MBBR. So all that possible expenditure involved, even painting the plant and even minor maintenance, contractor profits, sorry, third party analysis, certifications, all those possible costs were taken into account, and the present worth is being evaluated, and based on that present worth, the cost of treatment per unit of water is estimated. And you can see, if we have only primary and secondary treatment in place, the major component is the manpower salary, second major is the capital cost, and third major is the energy need. Whereas when we have tertiary treatment in place, with all three in place, the cost is marginally get escalated by a few paisa, whereas for only ozonation and ozone plus chlorination, the cost almost remains similar. So, considering all this cost, for 300 cubic meter per day capacity plant, the cost of per unit of treatment is coming to less than 16 rupees per kiloliter. And because of the smaller size, and when the plant is of 1350 meter cube per day, the cost is coming to less than 11 rupees per kiloliter. So our set target was 15 rupees, and we are able to produce treated water with nearly less than 11 rupees per kiloliter. And on our campus, the water supply that we do, it costs us about 27 rupees per kiloliter. So there is net saving of nearly 16 rupees per kiloliter of the water that we save and use it for non-potable purpose. So that will give us the revenue return model for this sewage treatment plant. So now here onward, the upcoming technologies which our lab is researching in the bio-electrochemical system, I will take you through a few more slides. So few of you may be aware of what it is. The concept has come up. First paper on microbial field cell has come in 1911. Second in sometimes in 1936. Third in 1960, and fourth in 1998, 1999. So in a century time, only 3, 4 articles were published. But since 1999 onward, there is a surge in the knowledge contribution, and you will get convinced when I will show you the publication record on this. So MFC is consisting of anodic chamber, where the wastewater works as a fuel. So when the wastewater is applied, it will come in contact with the electrogenic microbes which are grown on anode. So these microbes will oxidize organic molecule, convert it into electrons and protons. The electrons are passed through the external circuit towards cathode. Protons are allowed to pass through the proton exchange membrane, which separates anode and cathode. And this way, the cathodic chamber, generally it is aerated. So the oxygen present in the air will react with electron and proton to get it converted into H2O. So this way, the electron flow will generate the electricity flow in the opposite direction, and the external device that we would like to power. So that can be powered using this MFC concept. This microbial fuel cell have a distinct advantage. It can produce a sustainable green technology. It can be sustainable green technology while treating wastewater, generate electricity, which is stored in the chemical bonds of organic matter. High energy conversion efficiency is expected. It can be operated at ambient as well as at low temperatures. Less sludge production equivalent to that of anaerobic process. Does not require any off-gas treatment, because off-gas in anodic chamber is a carbon dioxide. No energy requirement for aeration, provided the cathode is passively aerated. So I will show you the pilot where the cathodes are air cathode. Though the technology looks exciting, but there are challenges. The individual MFC can give, single cell can give only up to, theoretically, though the voltage expected is 1.1 volt, in practice, it ends up giving only 0.5 volt. Because of the unavoidable losses, that is activation loss, concentration polarization loss, and ohmic loss, when any charge flows, some resistance it will have, and that loss will occur. So in practice, we end up getting about zero point 0.5, zero point 0.6 volt. And hence, scientists are trying to research on the materials which are involved in the fabrication of this device, so that efficient material, so that these losses can be kept as minimum as possible. Scaling up of the system is difficult due to involvement of bio-electrochemistry. So electrochemistry restricts It cannot be, as I showed you, USB reactor of 150 cubic meter volume. We Even if we have MFC of 150 cubic meter volume, it will generate only 0.5, 0.6 volt, and that voltage is a useless voltage for any practical application. So we need to have MFC in stacks so that we should be able to integrate voltage as well as current. The electrodes which are presently used, platinum is used as a catalyst to accelerate the oxygen reduction reaction, and that makes the fabrication way costly. The membrane separators, PEM, I talked about, the Nepion commercially available membrane cost about 1,600 US dollar per meter square. So that makes the fabrication very costly. Even the second runner, Ultrex membrane, that is also about 800 to 900 US dollar per meter square when we import it in India. So that makes fabrication cost 10 times more than the existing technology. And periodic replacement of these components will also add on to the cost of this device. This MFC or BS, bio-electrochemical system, has several applications in the life sciences. Apart from wastewater treatment, it can be used as an energy source for powering low power electronic devices, telemetry devices, or even domestic micro power needs like mobile charging devices. Mobile can be charged on this electricity generated. It can be configured for desalination. It can also be used for powering the medical implant devices in the human body. And here it will convince you the yesterday's statistics. I mean, though I said in till 1999 there were only 4 5 papers. So, but then onward, you see 16,500 nearly articles have been published in last 25 years. So that shows how scientists are paying attention for developing this technology. And this is our research group stands second in the world after Bruce Logan from Penn State University. And as an institute wise, we are at the fourth rank globally. First two are the Chinese funding agencies. And the institute wise, Harbin University, China is first, then Pennsylvania State University, Penn State College, and then IIT Kharagpur. So, based upon the collective research efforts from the various research scholars, since 2005 we started research in this area. Mainly, we contributed the replacement of costly polymer membrane with the ceramic membrane. Our natural clay, by spiking it with the 20% malt modulinite, the electrochemical characteristics of such ceramic membrane are similar to that of Nafion. And using those ceramic membranes that you can see in the red squares embedded here, so those ceramic membranes are way cheaper per square foot. It doesn't cost more than 15 rupees, and that way the fabrication of device becomes very low cost. So we also researched on the various non-platinum based cathode catalyst to enhance the oxygen reduction reactions. And with this collective effort, we came up with the concept, what we named it, and we patented it as a bioelectric toilet. So waste from the toilet will central chamber. Here it is visible in the horizontal photograph. So it will come to the central chamber. The central chamber is with combination with the aqueous cathode final chamber. It is MFC, and then on the periphery it has a 5 air breathing cathode containing MFC. So the black square that you see, this is a carbon felt that is covering the ceramic separator, and it has a parallel pair of anode inside, again made up of carbon field. So this way, 9 ceramic separators forming the membrane electrode assembly are installed on one panel, and these are working as a air breathing cathode. So air, oxygen directly from air is being utilized for supporting cathodic reaction. And while the wastewater admitted to the first chamber, when spills over, half flows clockwise, half flows anti-clockwise, and finally it comes to the aqueous cathode chamber, where hypochlorite is being dosed to work as a disinfectant as well as oxidant. And this way, this combination of wastewater treatment simultaneously facilitate the electricity recovery. We use different catalyst for academic investigation to find out performance. And here is the performance of operation for more than 2 years. BOD is nearly 23, so less than 30, meeting the then standards. COD less than 80, MPN also less than 100. And that way this water is suitable to be reused back in the toilet for flushing. So what we are doing in a day, once the treated from the treated water sump, the treated water is pumped to the elevated service reservoir above the toilet. And this way, once you flush the toilet, the equal amount of treated water is displaced from the system and getting stored in the treated water sump. The evaporation loss that is bound to occur in Kharagpur, we experience it in the range of 8 to 15% with the different season. This can get compensated with the water that we use for cleaning. So every use of toilet, we use half liter to 1 liter water. So this will compensate the evaporation loss, and that way it will make the this biolated toilet as a water-free toilet, because water will be continuously made available for flushing and for maintaining cleanliness in the toilet. So, and apart from that, the electricity in the process generated will be used for illuminating the toilet premises at night and toilet cabin at night. So, this way, fearless use of the toilet by ladies and children can also be supported at night, because they are typically afraid of the attack of insects or animals during night time. So we have another installation at the NTPC campus, Greater Noida. That also we operated for more than 1.5 years for treatment of sewage generated from their guest house, and this also gave satisfactory performance. We can configure microbial fuel cell to microbial desalination cell by placing a desalination chamber in between anodic and cathodic chamber. So wastewater can be treated first in the anodic chamber for removal of organic matter, and the same wastewater can be applied in the desalination chamber to facilitate desalination. Because of the charge difference between anode and cathode, the anion will migrate towards anode, cations will migrate towards cathode, and this way desalinating the either wastewater or saline water is possible. We did experiment with the Tata Steel wastewater with their own funding project using different salt concentration in desalination chamber. You can see the TDS removal ranges between 60% to 80%, and also the COD removal all along above 80%. And apart from organic matter removal and supporting desalination, it also helps in harvesting the electricity. So multiple advantage this MDC configuration can offer. And the last configuration, which I was talking about, the microbial electrosynthesis. So the carbon dioxide generated during oxidation of organic molecule can itself be captured again to convert it into value-added chemicals. So, or we can use the carbon dioxide from the flue gas also for synthesis of the chemicals. The concepts here are instead of harvesting electricity, we have to impose potential -7 to 1 volt potential if we impose on cathode. So that will take these CO2 reduction reactions forward using specialized culture. We can convert this into various carbon compound, 2, 3, 4 carbon compounds. In anodic chamber, either wastewater can be treated, or we can simply use water. So because of the imposed potential, some water splitting will occur, and that will make protons available for the cathodic reaction. Scientists reported formate, acetate, and ethanol with various concentration, and in our lab we could successfully synthesize acetate, isobutyrate, and propionate. Then we came up with 12.6 liter capacity MES. So the idea here was the biogas generated from the USB reactor will be passed through this MES system, so that the CO2, which is typically about 30% in our biogas, so that can be captured and converted into chemicals, and this way it will enrich the methane content in the biomass as well. And typically by passing the biogas through this MES, the methane, which is originally 65% approximately, is enriched to about 80%. So this 15%, nearly 50% reduction in CO2 is being achieved, and we successfully converted into 400 milligram per liter at that time. Now with the recent research efforts, the acetate yield we have reached up to 1.5 gram per liter. But still, for practical application, we need to enhance the acetate yield further by selecting a proper catalyst and by enriching the proper microbial culture. So with this, I will stop and look forward for public outreach, dissemination, replication of these technologies, and training manpower further. These are the books which I authored in the recent time: Wastewater to Water, published by Springer; then Micro Constituents in the Environment, published by Wiley; and also last December, Microbial Electrochemical Technologies, Fundamentals and Applications. Two volumes have been published by Wiley VCH. And I deeply acknowledge the hard work done by all our research scholars. So that only makes it possible for me to share whatever the results that I have presented today. So I thank to all of these young scholars for their scientific efforts. And thank you very much for patient listening. And if time permits, I'll be happy to take a few questions. Over to you, Dr. Govind.
Thank you very much, Professor Makrand Ghangrekar, for finding time from your busy schedule and participating in this conference. And it was very nice to read you,
Dr.
to
Kulkarni, you are
listen
mute,
you.
I think.
So, Professor Makrand Ghangrekar, thank you very much for your excellent speech. And it was always nice to listen your thoughtful lectures with full of wisdom. And because of the paucity of time, whatever questions are there from the delegates, I will pass it on through email. And thank you very much.
Thank you, and thank you for giving me a chance to be here. Thanks a lot, and
It's
have a great day ahead and successful conference.
our pleasure. Thank you very much. Bye.